basically the first question we have is that a to the power n, b to the power cn. So a to the power n and b to the power c to the power n. And now what happens is that you try to prove through pumping lemma that this is not regular. So for regular proof is pretty simple. We have u, v, w, that's it. These are the variables we have, and this needs to be less than equal to j, the bracket of this. And there is another rule that says that v, which is the pumping part, needs to be greater than equal to 1. These are the two rules that are very important for us to pump this. First of all, we need to find a word that we decide that is in the language. So a to the power j or a to the power p. So actually this is a p that we don't know, but we know the language itself. A and c are equal and b are constant. Basically it's the one b only. We have to decide a word that belongs to the language. I decide this word. Of course this belongs to the language. If I just do p plus 1, basically this means we add one thing to the language. In that way, if we try to say, let's imagine the j is 4, so it becomes 1 2 3 4 and 1b 1 2 3 4, and we did plus 1 here. Or even if we just take p as a word, what happens is that we can basically pump, because we know that in the regular pumping lemma this needs to be selected from here, and j is 4, which means this is 4, and the UVW needs to be less than equal to the j part, because here we said j equals to p and we already placed it here, and the value here is 4. It needs to only be taken from this part. So u v w needs to be only in this part, and once you pump this part it becomes bigger than the c. So all the decompositions, for example a bunch of a's and b's and a bunch of c's, in this way, if you take all a's, that's also fine. If you take some a's and some b's, we know that we cannot do this because this is bigger. You have to first take u, v, and then w, and it needs to follow a sequence. UVW needs to follow a certain sequence. It cannot be anywhere. In context free, it can basically be anywhere. He can decide anywhere to be UVW. But in this language, because the sequence of the language itself matters, we have first a bunch of A's, then B's, and then C's. And because all of the B's encompass of all the P's, which is basically our J, he must take everything from A's. This is not allowed. This is also not allowed, and this is also not allowed. So he can only decide from A's, and if he pumps A's while I equals to 2, then A's become more than C's. That was for the question number 1. Then we go ahead for question number 2, and we see that contains as many zeros as 1. So this is 1 1 1 0 0 0. So we say 1 to the power p, 0 to the power p, where we don't know what is j. He might say j is, I don't know, 3. In that way, we say 1 1 1 0 0 0. But because we have this, and we have this on entire, he must only take from this. So v, u, v, w needs to be less than equal to j, which is this in our case, and he needs to decide this from this, within this. He cannot make u, v, w wherever he wants. He needs to start from here, and maybe he wants to take this only 1. In v, he needs to take 1. In w, he cannot take all of this, because u, v, w needs to be less than equal to the j. And because j, in our case, we replace the j with a p, and if that happened, then this cannot be possible. The only decomposition that's possible is, if we see 1 2 3 4 5 6, our UVW needs to be less than equal to 3 in our case. So it can only be, UVW can only be here. It can only be here, where U can also be empty, but it needs to be only consisting of ones, and anything otherwise is not possible, like this, because in this way 1 2 3 4 1 2 3 4 we are taking, and 4 is bigger than 3. So it will always pump the ones, and once it pumps the ones, they become bigger than 0 0 0. Then we have the next question that says that the Duck theorem, and let's look at Duck and the 1-0 language. So the Duck theorem basically means that there is this bracket and this bracket and this, and what we can do is that we can put P on this, 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 where let's assume J is 3, where 1 2 3 1 2 3 1 2 3 1 2 3, and because all of these have P 1 2 3, it only needs to be pumped on this side, where I equals to 2 makes this 1 2 3 4 1 2 3. So this is 2 times now, and 1 2 3 4 5 6 7 8 9. Now these do have the closing one, but these opening don't have a closing one, and that's why this is not, this disobeys, and this is not regular. So if we cannot figure it out through the language, if the pumping lemma proof fails, it basically tells us nothing, but if the proof works, it tells us that it's not regular. It might be part of the other circle, so it's not regular type 3. It might be context free or maybe more smaller, but at least it's not that. That's what the proof tells us. And based on that, we can move on to the next question, which says 0 and 1 asterisk 0 comma 1 asterisk. Now be careful that I is what you decide, UVW composition is what he decides, word is what we decide. We decided word to be the P. We put P everywhere, and this is part of the language. We replaced his J's with P's, so he doesn't give us the J, but we can decide the word, and we can decide the I, and he decides the decompositions. But because we have the rule of UVW being less than equal to J, he cannot make a decomposition here anywhere he wants. That's only for the context free ones. That's coming up next. Now we have something like this that says that they are infinitely zeros and ones, 1 2 3 1 2 3, but because they are infinite many, there is no variable here, and this cannot be proved. This know is that this is actually regular, and how we know that is because of this. I can give a quick overview, because see, if the expression is this, it is infinite regular language, meaning that 0 or more repetition of the precedings of how many times we want. It is regular because you can represent with a simple DFA, a start state that transition between whatever, or a single state with 2 transitions. Finite languages are subset of regular languages, but not all regular languages are finite. Any language defined by a regular expression using the knee star is regular. So this is basically regular because it is finite language, and all finite languages are regular because they can be expressed or represented by a deterministic finite automation or simple regular expression. Even if it can be, and this is a regular expression basically. This is a regular expression which it contains 0 comma 1. Let's make a DFA for this and say that it has a start state and accepting state where 0 comma 1, and you can just loop this forever, whenever, however time you want. And because we can make a DFA of it, it basically is regular, and this is actually a regular expression. So that was basically it for that question. Now we're moving forward to the next question we have. Now we move forward. Now we have context-free ones. Now there is a difference between context-free ones. I can explain you in a minute. But we first look ANBM. ANBM CNDM. Here we have a clear pattern. A is equal to C, B equals to D. So the amount of A's are equal to the amount of C's, and the amount of B's are equal to the amount of D's. What that tells us is that, for example, we can choose a word, and our word is, now this is of course J then, and he never gives us the J, he knows it, but we can cleverly decide a word that is J itself, that consists of J, and that is in the language. Now we will need to look at the possible decompositions. Now remember, context-free pumping lemma is different. The only difference we have is that he can decide any decomposition anywhere. He can even say 0 in U or 0 in W, or make it anywhere in the word. But the only rules that apply is that V, U, V, W, X, VWX are less than equal to J, and V and X are greater than equal to 1. Now because we know, let's imagine there are a bunch of A's and a bunch of B's and a bunch of C's and a bunch of D's. He can decide to put his UVW composition anywhere basically, but he must make at least one V or at least one X. That's the rule. But what he can do is that he might take a bunch of A's only, and if he pumps that, we can say I equals to 2. If he pumps these, then the word breaks. Because then A's are not equal to C's, because A's become more. That's the one possible decomposition. Only A's. Second is that some A's and some B's. This is also possible decomposition, because we don't know if he took one A or one B only, which is again less than J, because J could be 3, let's suppose. Then 3 B's, 3 C's, and 3 D's. And this is still, he can take one from here and one from here and make everything else 0. He can make U 0. He might not. This is also the case. This is only the case in the context-free one. He can make U 0. But in the other languages, he cannot do that. He cannot make U0 or W0. In this, he can do that. And if he makes U0, he can take these two, and these will be counted as a 2 instead of the 3, which will not obey this one. In that case, we still don't know. And if he pumps this, this is a possible decomposition. But if we pump this, then A and B become more, and the count of these remain the same, where B and D should be the same, while B become more and D remain the same. This again disobeys our language. Then we might try something different. If he takes a 1A and 1C, because the order of the language tells us a lot about everything, the order is that A, B, C, D. So if he takes 1A and 1C, he must have taken all B's. This is a guarantee that he took an entire J, which is of course not possible. This makes it bigger than J, because J plus 1 is more than J. This is a disobedience of the rule. And that goes with all other combination where he might take one here and one here. This also disobeys. So these decompositions are not allowed. This is cheating. Then if he tries to take all of this at once, of course this is cheating again. So these decomposition will not be allowed, and with all the possible decompositions, the word is already breaking when I equals to 2, because we can decide the I. Then we have W hash W, where we have AB, W hash W, and A comma B, meaning that if we have AB, then hash AB, it repeats on the other side. So we can say a to the power p, b to the power p, hash a to the power p, b to the power p. Now what happens is that we can look at possible decompositions. He might say, I'm going to put all of the u's 0 and I'm going to take only this and I will pump it. In that case, this will not be equal to this part, which will again disobey the language, and this decomposition where I equals to 2 will break the rule. Then he might say, okay, I will take this. This again means he took this and hash and a, which is definitely more. So taking one part from here all the way one part here guarantees that he took all of the, he took more than one. For example, if we say, because this already has a p, meaning that you took a p and you took another p plus you took this. This is not possible. Plus 1. You also took this and you also took this, you also took this, which makes the hand very big. It again disobeys the law. And this decomposition is again not allowed because it's taking an entire, let's say j equals to 2. So AABB hash AABB. This means you took all the B's and all the A's. This had, of course, a clear P on it, and this had a clear P on it. You cannot take even a single one of this without making sure that you guaranteed definitely took some P's from the other one. And you definitely took more P's. This basically proves the fact that you're taking P plus 1, which is more than P. This guarantees basically. This decomposition is again not allowed. And if you were to take all of this, this is again not allowed. Hence, the only one possible decomposition is taking either A's alone or either B's alone, which again disobeys the language. Then we have the other one that says a to the power n, where n is a prime number. Now we have first question, a to the power n, where n is a prime number. And we know that prime numbers are basically numbers that only appear in their own table and nothing else. Now to make this not a prime number, we have to make it a composite number which appear more than itself, more than the tables of itself. And how we do it is that we make a to the power p first, and then we say a to the power p plus 1. Why we do it is because this is going to help us to factor out for factorization reasons. Let's assume the j was, I don't know, 5. But in our case, we don't even need to assume it. We will do all of this proof through algebra. We know that u, v, w, x, y, the length of this plus length of this plus length of this plus length of this, and plus I minus 1 plus length of v plus length of x. This is the same thing. So because we did plus 1, we can go one step back, minus 1, and we can plus v and x like this. It's the same exact thing. You take one step back by minusing it, and you take one step forward by plussing it. So this is the total length, of course, in algebraic format. In that way, we know this is basically our r, which is the total length, or p, you can say. This is our p, and this is r. And if we pluck the value of I, which p plus 1 minus 1 as it is, and we put bracket here, then we put plus here, the plus that we had, we can basically get rid of this part, and then we have p plus pr. We can then factor this Why we were doing this? Because we need to bring this in the form of a multiple instead of addition. That's why we need factorization. And then we can just factor this by saying, taking p common, we take p from here, we're only left with 1. We take p from here, we're only left with r. This will guarantee a composite number because both terms will be bigger than 1. If both terms are bigger than 1 and they get multiplied, they will always yield a composite number, in having a multiple one of itself and then other kind. Meaning if p, it needs to be something because it's bigger than equal to 1. And here 1 is being plus 2, at least bigger than equal to 1. So r, we have the rule that the length of v plus x needs to be bigger than equal to 1. This is also a rule. When we have that rule, it's plussing something with 1. 1 plus 1 equals to 2. And 2 times, even if it's the minimum at 1, then it will always get multiplied with more than 1. And in that way, we will always guarantee to have a composite number like this with this formula. Then we have the next question, which says a to the power n, a to the power 2 to the power n, to the power n. These are multiples of 2 or 2 squares. Let's assume that we can first say 2p to the power p, and we can say is less than 2 to the power p plus r, which is less than 2 to the power p plus 1. This is our 8. This is our next term, p plus 1 meaning 16. So this, our word basically, the word that we decided is 2 to the power p plus r. And how that breaks is we're gonna show that how that breaks our condition, and it proves that this is not context free. We did it 2 to the power a to the power 2 to the power p plus r. What it did was that we know that, imagine if this is 8, 1 2 1 2 1 2 1 2 3 4 5 6 7 8. So I equals to 1 here. Now we set I equals to 2. We can decide the I. This is what we can decide. Once we do it, then this gets plus with the overall length, which is our new length, which is AA. This is our new length, AA, and AA, which is 1 2 3 4 5 6 7 8 9 10. And 10 is falling somewhere here in the middle. It will never reach the next square, always when we have I equals to 2 with this formula. And our word that we decided was a to the power 2 to the power p plus r, which basically broke our law. Go a little bit more into depth of this question, that a to the power p to the power p. Now we can say that, let's assume that j equals to 3. 1 2 3 1 2 3 hash 1 2 3 1 2 3. Now we know that VWX can be is entirely within the first W, allowed by rules, but results in a string where first half no longer matches the second half. So it's entirely here. In that case, this will be pumped where I equals to 2. We can decide, and when we do it 2 times, then this is not equal to the second half. Then the other decomposition is that contains the hash. Pumping will either change the number of symbols on one side of the hash or potentially remove the hash entirely, violating the condition structure. So we might also take something like this, but this will again remove the hash and the structure will again be broken. Then VWX can be entirely within the second W. So it can be either entirely here. The only thing that is not allowed is that it spans all over the place. This is just not allowed. It strands both the first and the final B simultaneously, meaning it takes all of this and all of this. This is of course impossible because this means that you're taking all the P's guaranteed and you're taking all the P's guaranteed on both sides. So if this is a guarantee that you disobey the rule. I mean, of course you can take this and this will never, we will never know if you really disobeyed it. But even if you pump this I equals to 2 times, where you take this Vx as W, then this again, I equals to 2, this becomes BB, and the rest remains the same. B, B, A, and here you pump the A 2 times, and the rest comes here, A, B, B, B. Let's look at it. Separated by a hash. These are 3 A's, but these are 4 A's. These are 1, 2, 3, 4 B's. These are 3 B's. So this also breaks the structure of the language. And the only decomposition that's gonna keep the word is you take all of this. But this is not allowed because then it is guaranteed that VWX is bigger than equal to J, which is not allowed.